So good morning students. So we'll be now starting with module 4 virtual memory concepts. Okay, so here in this video, so we will be learning about the what is the virtual memory, so what is the background necessary for virtual memory, so how you are executing the programs. Okay, so this is the general background, okay, so of your execution of your program. So then we'll be knowing what is your demand paging. Okay, so then we'll be learning, okay, so what is your copy on write. Okay, so what is the page replacement algorithm. Okay, so how allocation of frames will be done. So then we'll be learning about the thrashing. Okay, so here we'll be ending your chapter with a thrashing. Okay, so the objective here is to describe what are the benefits. Okay, so what are the main benefits of your virtual memory system. Okay, so to explain this, so first we'll be beginning with the concept of what is your demand paging. Okay, and then we'll be learning what is a page replacement algorithm and how allocation of frames will be done. So after that we'll be discussing, okay, about the working set model. Okay, and we'll be examining the relationship between the shared memory and the memory mapped of files. Okay, so now here the background. Okay, so what are the basic things which are necessary for you to understand, okay, about a virtual memory. Okay, so we know that generally we will be bringing the entire program, okay, into the memory, so for execution. Okay, so your CPU will be fetching one instruction, okay, by instruction from the memory, okay, into the IR, and then it is decoding that and executing it. So like that, after doing that, it is again fetching one more instruction. Okay, so now we know that all the entire program code is not needed at the same time. Okay, so sometimes the program can have a error code. Okay, so we may be writing in the program, so we are writing the exception. So in the exceptions we'll be writing, okay, if that exception is occurring, so what is the error to be displayed. So this is the error code. Okay, so sometimes some routines are there. Okay, so as a precautionary measure we are taking that routine, so that routines are not being usually used, so we are having unusual routines. Okay, and we may be having large data structure. Okay, so from the large data structure we are using only a little bit of your data structure. Okay, so what we do, we are using the arrays. Okay, so arrays we declare normally the 100 elements. Okay, so all the 100 elements are not being utilized at the same time. Okay, so this gives an idea that the entire program, okay, is not being used at the same time. Okay, so entire program need not be used at the same time in the main memory. Okay, so that means we are getting to an idea that, so if required, okay, if any facility is there, so where we are getting only the portion required to be executed, so only that part of the program will be brought into your main memory. Okay, so now this is creating the ability to execute partially loaded program. Okay, so some part of the program is still there in the hard disk, another part of a program so is loaded into the RAM or to your physical memory. Okay, so this ability is a great advantage. Okay, so where it is giving us the advantage that, so program no longer is constrained by limits of physical memory. So that means that, okay, your RAM or your physical memory, okay, is not restricting you from the program size. Okay, you can write program, okay, so whose length of your program, the size of your program can be larger than the size of your RAM. Okay, but the program size cannot be larger than the size of a disk. Okay, so what we do, we get required portion into your RAM and then executing it. Okay, so this is a very great advantage, so where we are not restricted from the size of your physical memory. Okay, so now this is a very great advantage. So this advantage we are going to use in the virtual memory concept. Okay, so another point, so each program takes less memory. Okay, by having this, okay, by having getting only the little portion of the program, okay, loading into the memory, okay, only less memory is consumed, so which is giving a chance for more number of programs to be loaded. Okay, so partially loaded into your RAM. Okay, so that means you are getting a capability of executing it, okay, and then you are loading the partial program, so more number of programs can be loaded into your main memory at the same time. Okay, so that means your utilizing CPU utilization is increased. Okay, and throughput will also be increased. So we know that throughput is number of programs executing per unit of time. Okay, so your throughput is increased, your CPU utilization is increased. Okay, so without increasing in response time or turnaround time. Okay, so this advantage of partially loading your program, okay, and which is, okay, not restricting you, so you can write the lengthier programs. The programs can be greater than the size of your physical memory. Okay, so now by this you are giving a chance to load more number of programs in the memory. Okay, so which is increasing your CPU utilization and throughput without increasing in response time or turnaround time. Okay, and less IO input and output is needed to load or swap programs into memory. Okay, so because you have, instead of having the entire program, you are getting only the portion of the program, so less input and output is needed for swapping the programs in to the memory from the hard disk, okay, or swapping the programs, okay, out from your physical memory to the hard disk. Okay, so your programs keeps on moving between the physical memory and the disk. Okay, so as and when required, so which is requiring because your size, a portion of program or is partially loaded, so your IO needed is also less in this case. Okay, so this is the advantage of loading the portion of the program. Okay, now virtual memory. Okay, so virtual memory, so this means that, see, virtual means what? Literally virtual means not existing. Okay, so virtual means not existing. Okay, so virtual memory means the memory which is not existing. So this is to say that, okay, so we are going to execute our program, okay, where the program size is larger than the size of your physical memory. Okay, so that means, okay, so let's just see here example. Okay, so I may be having, okay, so I am okay, I'm having a program, okay, so whose size, okay, so size of my program, okay, so you take this to be having a 6 GB of my program is there. Okay, so we are having a 6 GB of the program. Okay, so whereas your RAM is only consisting of, okay, so maybe it is consisting of, okay, 5 GB. Okay, so 5 GB of RAM is there. Okay, so you have a 5 GB of RAM. In that 5 GB of RAM, okay, so you are having, okay, operating system is given some space, okay, and the rest of space is for the user. So if operating system, suppose take example, it is given, okay, so 2 GB, then the rest will be given 3 GB for the user program. Okay, now you have a capability of executing a program whose size is 6 GB, okay, but, okay, which is larger than the size of your RAM, so the area which is given for the user. Okay, so this is a concept where the program is larger in size but still capable of executing in the RAM which is lesser in size. Okay, so this is called, we are calling it as a virtual memory. So this concept we are calling it as a virtual memory. So how are we doing this? So we are not loading the entire program of 6 GB here. Okay, so we load only the required portion of the program. So this is, okay, so what is going to allow, okay, execution of a program which is larger in size, okay, so compared to the size of your RAM, okay, or a physical memory. Okay, so now this is going to clearly separate, okay, so this is going to clearly separate the user's logical memory from physical memory. So user's logical memory was large and physical memory was less. Okay, so there is a clear separation between the user's logical memory and the physical memory. Yes, only part of the program needed to be in memory for execution. Yes, so only you get portion of the program which is needed, we are bringing that into your main memory. Yeah, so now we can have logical address space, so which is belonging to the user's view can therefore be much larger than the physical address space. Okay, so the address space, okay, can be shared by, now because we are getting some portion of the program, so we can have many more programs, okay, in such way loaded into your RAM. Okay, so now the address space of your physical memory, your RAM, is shared by more number of processes. Okay, so it allows more efficient process creation. Okay, so more programs can run concurrently, so because portion of program is loaded, okay, so we have less input and output needed to load or swap the program. Okay, now virtual address space, okay, so logical view, so logical view is, okay, is not the system view, Okay, logical view of how process is stored in the memory. Okay, so that is virtual address space is belonging to the program's actual address space. Okay, so usually it starts at 0, so we assume it to be contiguous address, okay, until the end of the space. Okay, now actual physical address space is the space of your RAM, so which is organized into a frames. Okay, now we have memory management unit which maps your logical address to physical address. Okay, so virtual memory can be implemented via demand paging and demand segmentation. So using these two concepts, so we are able to execute a program which is larger than the size of your RAM, greater than the size of your RAM, but still capable of executing it. Okay, so which techniques we are using to implement a virtual memory is demand paging and demand segmentation. So these are the two techniques using which we are going to implement the virtual memory concept. Okay, so here you can see that, so this is my program. Okay, so this is a virtual memory, so where we are having page 0, 1, 2 and so on till page n. Okay, so like that you can see the size of your physical memory is much less. Okay, so this physical memory is storing the pages of all the other process also. Okay, so now the size of this is very less compared to this. Okay, so now you have memory management unit which is mapping the pages of this, okay, to the physical memory. Okay, so some pages, some portion of this virtual memory, one portion of your user process, okay, is loaded here, and the rest of the pages are available in your hard disk. So this is how you are going to implement the virtual memory concept. Okay, so now let's, before beginning to the other concept, so we'll see what are the contents of the user's program. Okay, so we say the program is larger in size. Okay, so what are the contents of the user program? Okay, so the virtual address space, so it is designed, okay, so logical address space for you have a stack. Okay, so you have a heap. Okay, so we start a stack for the maximum size, so it is growing down. Okay, so we just reserve some space for stack, so in case, okay, so while this while executing, okay, so there are chances that the stack, okay, is growing. Okay, now we start again reserve some space for as a heap, so this portion is normally used for implementing the dynamic variables and all. Okay, so this will be growing upward. Okay, so this will maximize the address space use. Okay, so if any page is increasing, suppose this is allocated some space, if it is growing, okay, so any new page is required at runtime, so you will be left out with some hole here. Okay, so that hole can be utilized. Okay, so unused address space between these two, okay, is a hole, so no physical memory needed until these two has grown to a particular new page. Okay, so we just reserve some extra space when it is growing, so that time you require the extra space. Okay, now this is enabling the sparse address space with hole left for growth. Okay, so the sparse means it is not contiguous. Okay, so it is a hole, so dynamically if you are needing an extra memory, so that will be allocated from this. Okay, now you have system libraries shared via mapping into the virtual address space. Okay, so system libraries, like you are using the hash include stdio.h, any other header files you're going to have. Okay, so all those will be mapped to this, so that means you are not creating the space for that here. Okay, so this is not a part, those libraries are not part of the virtual address space of the user's program, so they are a program whichever is using those libraries will be mapped with the virtual address space. Okay, so shared memory by mapping pages, okay, read or write into the virtual address space. Okay, so any shared memory you're going to have between one process and the other process, so that also will be mapped into the virtual address space. Okay, so now pages can be shared during the fork. Okay, so speeding up the operation. Okay, if suppose you are having a parallel programming, in that you're creating a child process and all, so you know that some of a pages, some of a code of parent process and a child process will be normally same, so those pages, okay, can be shared between the parent process and child process. Okay, so now here you can just visualize, you have a stack. Okay, so you may have a shared library. Okay, so you may have shared pages which is shared between the two processes. Okay, so you have a heap, you have a data section for one process, code section for one process, so separate heap, data and code section for another process and the stack. Okay, so you can share the pages which are common between the two process. So like this, okay, so you are just utilizing, better utilization of memory is being done. Okay, so now demand paging. Okay, so we said virtual memory concept is implemented using the demand paging and demand segmentation. So we have seen what is paging in the previous videos, okay, so the previous module, and we have also seen what is the segmentation in the previous module. Okay, now here we will have to know what is your demand page. Okay, so now we can normally we can bring the entire process into memory at load time, okay, or bring a page into memory only when it is required. Okay, so bring a page, this is more important, bring a page into memory only when it is required. So that means bring a page into memory only when it is demanded. Okay, so what are the advantage of bringing the page when it is demanded? Okay, bringing a page into memory only when it is needed. Okay, so less input and IO is needed here. Okay, so less input and output IO is needed. Okay, so no unnecessary IO will be required. Okay, so less memory is needed. Okay, so faster response will be there, and you have more users. More users can be accommodated because you're getting only the pages when it is demanded. Okay, so this concept of demand paging is similar to your paging system with swapping. Okay, so now page is needed. Okay, if it is there, you refer to it. If it is not there, it will be an invalid reference. Okay, so that current instruction will be aborted, and then till that new page, whatever is required is there on the hard disk, will be brought. Okay, it is not there in the memory, so bring to the memory. Okay, so for that you have a swapper called, you are calling that as a lazy swapper, which never swaps a page into the memory, never brings a page into the memory unless that page will be needed. Okay, so that swapper you can also call that as a pager. Okay, because it keeps on swapping the pages from hard disk to the memory, so it is also called as a pager. Okay, so now here you are having program A, program B in the main memory. So in the hard disk, okay, all the pages of your programs will be also there in your hard disk. Okay, so now suppose, okay, so program A has finished its execution, so you can swap out these pages there, okay, and swap in the pages for program B in the memory. Okay, so only required pages is brought in. Okay, if suppose if extra pages are required for program B, okay, then you can utilize this space, okay, by swapping out this and bringing the pages required by program B into this location, because this can be freed because those pages are not being utilized right now by program A. Okay, so like this we are going to implement the demand paging. Okay, now basic concepts what we have to know about the demand paging. Okay, so is with the swapping, so pager guesses which pages will be used before swapping out again. Okay, so like in the previous example, okay, so previous example I just said. Okay, so now suppose, okay, you think that here, okay, so initially program A some pages have been brought, okay, and program B some pages have been brought here. Okay, now suppose, okay, so program A has finished its execution, okay, or some of our pages is not being utilized for a long duration of time. Okay, so program B 3 pages were brought and executed, so right now it is it needs some more page. Okay, so which was swapped in. So now for that there is no space, all the other pages has been allocated to some other process. Okay, so now you can swap in some of our pages. Okay, so if there is no free frame, you are going to create a free space by checking out those pages which was not used for a long duration of time. Okay, now before, okay, so if it was not used for a long duration of time, then you can replace this, okay, with a new page. Okay, because there was no space, now this has to become a victim, this will be moved out, another page will be moved in. Okay, now before moving out, the operating system or a swapper or your pager has to clearly check whether that page was modified or not. Okay, so if it was modified again, so it has to copy the contents of that into the original location here. Okay, or suppose that page will be used in future, okay, in near future by program A. Okay, in that case again you will have a problem created by program A. Okay, so all these questions have to be posed before it is swapping in and swapping out. So because see, swapping in and swapping out, okay, so again you should not create extra problems. Okay, so that immediately again program A is requesting for a page which was just again swapped out recently. Okay, so these are the things, what questions, what the swapper or a pager has to guess, okay, which is a right page which it has to swap out, because it should not happen that just now it has swapped out some page, again a future memory reference, again it is requesting for the same page. Okay, so this it has to clearly check and then it has to swap out. Okay, so instead, so pager brings in only those pages in memory. Okay, so whichever is required it gets it, but before swapping some other page it has to think twice whether that will be needed in future. Okay, now how to determine, okay, the set of pages. Okay, so now you need a memory management functionality to implement the demand paging. Okay, so that means how to determine which are the set of pages which need to be brought. Okay, so how to know that with the pages which are to be demanded. Okay, so this functionality have to be modified in the memory management unit. Okay, now if pages needed are already there in the memory, so that pages we are calling it as a memory resident pages. Okay, so it is no different from non-demand paging. Okay, if pages needed are not memory resident, okay, then you have, what we have to do, if page you're going to refer that is not there in your main memory, then what to be done. Okay, so you have to detect and load that page into memory from the backing store or your disk. Okay, so without changing the program behavior, without programmer needing to change the code. Okay, if it is not memory resident, then you have to find out the where that page is existing in your disk, where is the location, where is it, say, where is it residing in the disk. So from there that page has to be brought. Okay, so that you service. Okay, without changing the program behavior. Okay, and without changing any of the code. Okay, now here, to know whether that page is a memory resident page or not a page. Okay, if a page is memory resident, so we are having that bit valid or invalid bit set for that. So if it is V, it's indicated that that page is there in the memory and it is memory resident. If the page is not existing in the memory, so it is not memory resident. So we are giving that as a I. So to say that it is a invalid reference. Okay, so initially valid bit is set to I for all entries for pure demand paging. That means no page is there, so all the bits will be set to I. Okay, whenever the pages are brought into main memory, okay, so it is in memory, that becomes memory resident. For that we are going to change that bit by to from I to V. Okay, so during memory address translation, if valid or invalid bit in the page table entry is I, then it is a page fault. So page fault means you are trying to refer to a page which is not existing in the physical memory, so that is called as page fault. Okay, you are trying to access a page, you are trying to refer to a page in the physical memory which is not existent. So how do you know it is not existent? Because the bit is showing invalid. Okay, so trying to access a page which is not there in the memory is called as a page fault. Okay, so this term has to be very clearly understood, what is a page fault. So trying to access a page, okay, which is not there in the memory, the page is not there in the memory, it is non-resident in the memory, so that, okay, is a page fault. Okay, and just have a look at this diagram. Okay, so we have a logical memory of a user's process. So we are having pages 0 to 7, so 8 pages are there. Okay, so page table, you can see page 0 is stored at frame number 4. Okay, at frame number 4 you are having a page A. Okay, so now this is valid because it is existing. So page 1 we don't have any entry, it is invalid. Okay, so likewise page 2, okay, it is stored at frame number 6, so it is, see here it is stored in the 6th frame. Okay, so likewise these are invalid entries. So page 5 is stored at frame 9, so we are, that is valid, is stored here. So we have only page this thing 0, page 2, okay, and page 5, okay, so stored at frame number 4, 6 and 9. Okay, so these are the pages which are brought in the memory, and the other, all the pages will be there in the hard disk. Okay, so your hard disk, once you save a program, the entire content is there. Okay, so now when we are bringing the required page, that means a copy of that will be brought here. Okay, so when you save a program, so all the parts of programs are available in the hard disk. Okay, so required pages are brought, a copy of that will be brought into the main memory. So this is how your demand paging is shown with a table. Okay, so now how do you go about a page fault? So whenever page fault occurs, okay, what the operating system has to do, okay, this is very important. Okay, if there is a reference to a page, okay, with first reference to that page will be trapped to the operating system. Okay, so if there is a reference to a page with pure demand paging, first reference to that page will be a trap to the operating system, so it is a page fault. Okay, pure demand paging says that we don't have any pages initially in the main memory or physical memory. Okay, so pages will be brought on demand. Okay, so first reference itself will be a page fault. Okay, now what the operating system has to do, this is very important question from exam point of view. Okay, so operating system looks at another table to decide, okay, invalid reference or abort. Okay, so it is not just in the memory. Okay, now it has to take care of some of our measures to do the page fault. Okay, find free frame. Okay, so free frame can be, now when there is a page fault you have to bring a page from the hard disk to the main memory. Okay, now where do you get and fit that particular frame into main memory? Okay, so you have to search for a free frame. Okay, if there is a free frame, allocate that page to that free frame. If it is not there, then you have to what we have to do, okay, that is next, swap page into a frame via scheduled disk operation. Okay, so you get a free frame not there, then select some page, swap that out into backing store. Okay, and in that location you load the new page. Okay, now before you swap out, okay, you have to make that page which was already there, that victim page is a valid entry from V to I, and now in the page table of a process, okay, for which you have brought the page, there the invalid entry will change to from I to V. Okay, so reset the tables to indicate page now in the memory. So set the validation bit to V. Okay, so now restart the instruction that has caused the page fault. Okay, so these are steps how the operating system is going to handle. Okay, so this diagram is important. Okay, so now load M. Okay, so this page was not there. Okay, this instruction is executed, this page was not there. Okay, so now this is an invalid entry. Okay, so when it is invalid entry, this page is not existing. Okay, so from the page table you have found that this page is not existing because it is showing I as invalid entry. So this is a trap to the operating system. Okay, so this is a trap to the operating system. Okay, so there is an error. Now what the operating system will do, it will search for that page, okay, on the backing store. So it has found that page. Okay, now it has to bring that page into the bring that missing page, okay, so into the physical memory. Okay, so where it is bringing in, it will find a free frame. Okay, so it will find a free frame in that place it is bringing this missing page here. Okay, and after that, okay, so this is going to update this I to V. Okay, because that page is brought, free frame was available, so it has brought. Okay, suppose if frame is not available, then another two scenarios will come. Okay, select a free frame. Okay, if that is belonging to some other process, that page table of other process has to be updated. Okay, if free frame is directly available, so then just get into this, okay, and refer this whatever frame number it is having, that entry you have to show it here. Suppose if this is a frame number 2, okay, so this entry 2 will come here. Okay, and then you are changing this invalid bit to valid, stating that the page fault is service. So this diagram is very important. Okay, so you need to explain steps in adding a page fault by drawing the diagram. Okay, now what are the aspects of your demand paging? Okay, what are the other issues, okay, of the demand paging? Okay, extreme case, what happens? Start process with no pages in memory. Okay, so every instruction will be a page fault. So this you are calling it as a pure demand paging. Okay, so every instruction is a page fault. Okay, so next reference will not be a page fault, first reference will be a page fault. So this is you are calling it as a pure demand paging. Okay, so next is, okay, actually a given instruction set could access multiple pages sometimes, so that times you'll have multiple page faults occurring. Okay, so now like you are having a block read, okay, you are having increment or decrement instruction, or you may be adding two numbers from memory. Okay, so two numbers from memory and storing that result back into memory. So this you will have whenever you add two numbers, okay, so you are actually referring to two memory locations, so two times to access for that particular data. Okay, so that is you are having a multiple page faults if those two values of those variables are not available in the memory. It is there somewhere in another page. Okay, so in the data, you must have seen the virtual address space, there we had some space shown for data, it is there in some other page. Okay, now that is again creating the multiple page fault. Okay, and other thing, what are the other things of the aspects of demand paging is, so you require a hardware support needed for demand paging. Okay, so what are the things you require? You require page table with valid and invalid bit entry. Okay, so page table is again a table in the memory. So secondary memory, you require a swap device with swap space. Okay, so that means in the hard disk you are not only storing a program, you need to have a separate space. Okay, so where the is so that you reduce the input and output. Okay, you have a separate space for swapping in the process whichever is executing, so that entire process will have to be brought into the swap space. Okay, and then you have to again start the instructions to be started. For this you require a hardware support. Okay, for implementing the demand paging. Okay, so like here you may have a multiple page faults whenever you are having a block move kind of instruction, or you may have a multiple page faults whenever the auto increment or decrement instruction is executed. Okay, so here you have to restart the whole operation. So here in the operating system has to be very careful how to service the page fault. Okay, now how do you judge the performance, how the performance of a pure demand paging can be achieved? Okay, so this in the worst case. Okay, so first step, for every reference will be a page fault, so this will be a trap to the operating system. Okay, now whenever it is trapped to the operating system, the user mode is changing to system mode. Okay, now whenever you switch on to from one mode to the other mode, you have to always save the state of the user register and process state. Okay, whichever process has given a page fault, so that means it is actually like interrupt your service, that interrupt is actually giving you the page fault, running the page fault service routine. Okay, so user registers have to be saved and process state have to be saved. Okay, and then determine that the interrupt was a page fault. So this, okay, or if it is a trap, it is a interrupt. Okay, that is nothing but a page fault. Now check that page reference was legal and determine the location. So now you require that page, so it is legal, so that you have to find out the page location on the disk. Okay, and after that, after finding out the location on disk, and now there is a disk responsibility to do the further actions. Okay, now the disk will read, okay, from the disk to a free frame. So that means it is requesting for a read operation from a for a free frame. So that means it has to find out, it is reading, okay, a list of free frames. So it is to find out where is the free frame available in the physical memory, so that the page required can be transferred from disk to the physical memory. Okay, so time being, if the request was not serviced, so that disk has to wait in the device until the read request is serviced. Okay, so after that it has found a free frame. Okay, then it has to again wait for a device. Okay, so for a seek or latency time, you know that the hard disk is implemented making use of your sectors, tracks and all. You have a head movement. Okay, so your head arm, okay, under that your sector has to rotate and come onto that. So all this is searching for the exact location of your sector. Okay, and for rotation, all this is a latency. Okay, so first it is reading for a free frame. Once it is found, again some time will be spent on device seek and latency time. So after that, so once your desired page is under the arm of your head, then the page will be transferred from hard disk to the main memory. Okay, now during this operation, okay, so CPU may be should not be idle. So till that time CPU may be running some other process. So once this operation, okay, so when the disk is ready to transfer the page, okay, so it will receive an interrupt from the disk. Okay, so this will indicate that it is ready for transfer. Okay, so now after that the transfer can be accomplished by transferring that page. Okay, so for that also, so CPU was busy with some other process, that process will be again have to be suspended. For that it is saving a register and process state for other process. Okay, and now the page will be exactly transferred. So now the interrupt now it is interrupt first from the disk. Now correct after transferring that page, so correct the page table and other page table, okay, to show that the page is now in memory, okay, because you have brought the missing page from the hard disk to the main memory, so you need to update the page table. Okay, so wait for CPU to be allocated to this process again. So after that page table is updated, then it has to restart its instruction after getting the chance for running for the particular process where the interrupt was occurred or a page fault has occurred. Okay, then you restore the user register, process state, new page table, okay, and then resume, okay, the interrupted instruction by starting it. Okay, now here you can see how the performance of your demand paging can be implemented. Okay, so here we can see that performance of demand paging, you have three major activities. Okay, so service the interrupt. Okay, so whenever page fault has occurred, okay, how to service that particular interrupt. So carefully coding must be done. Okay, so you may require many instructions. And read the page, so it will take a lot of time for reading a page from a disk, okay, to the main memory. So after that you have to restart. So these are the three major activities what we see. Okay, now page fault rate, so P, we are calling it as a page fault rate. It always lies between 0 and 1. If P is 0, no page fault. If P is 1, every reference is a page fault. Okay, so with the pure demand paging, yeah, so we have every reference as a page fault. Okay, so P is 0, no page fault. Okay, now always practically you may have a value of P lying between 0 to 1. Okay, now how we calculate the effective access time? Effective access time, okay, when no page fault has occurred. Okay, if P is a page fault, then no page fault will be 1 minus P into the memory access time. Okay, plus if page fault has occurred, okay, if P page fault has occurred, okay, then we inquire, along with this we need to also consider what is the page fault overhead for service page fault service routine, what is the time taken for swap page out and swap page in. Okay, so to swap out some page because free frame was not available and swap in the desired page, so for this also you take some time. So this less time is taken for these two, but more time is taken for this particular page fault servicing the routine and updating the tape. Okay, so now just consider here, so we have memory access time as 200 nanoseconds. Okay, so average page fault service routine is 8 milliseconds. Okay, now effective access time is 1 minus P, so P is a page fault, 1 minus P into 200 memory access time plus P, okay, page fault overhead, so service time, it is entire time total, it is given it as 8 milliseconds. Okay, so previous formula, okay, we have just seen it. Okay, so here page fault overhead, so plus swap page out swap page in, this entire thing is 8 milliseconds in this example. Okay, so 8 milliseconds, so 1 minus P into 200. Okay, so memory access time for no page fault, so then plus P if page fault is occurred. Okay, then what is the page fault overhead? Okay, now 1 minus P into okay, 200, so actually we have this should be a bracket. Okay, so 1 minus P into 200 plus P into 8 milliseconds. Okay, now this is nanosecond, so 8 milliseconds will be converted to nanoseconds. Okay, so 200 into 1 we get 200. Okay, plus, okay, now we have 200 minus 200 P plus, okay, this value of P. So with those things have to be evaluated, then you will end up in this value. Okay, now if one access out of 1000 causes a page fault, okay, one access out of 1000. Okay, so if you have one access out of 1000, okay, so we have a page fault. Okay, so then, okay, your P will be equal to, okay, so one access out of 1000, okay, is a page fault, so your P will be equal to what? Okay, so this will be equal to 0.001. Okay, so one access out of 1000 is a page fault, so that means 1000 times you have access, and in 1000 access 1 is a page fault, one time you get a page fault, then P value will be equal to 0.001. Okay, then substituting this value here, okay, and then whatever value you get in nanoseconds, convert that to microsecond, then we'll be having effective access time to be 8.2 microsecond. Okay, you can substitute this value here, okay, and then calculate this value you get in nanoseconds, that you convert it to microseconds, you will get it as 8.2. okay, so this will slow down by a factor of 40. okay, so like this we will be getting the calculating the effective access time. okay, now how do you optimize the demand paging? So that means optimize the demand paging means that you how is that the effective access time can be improved. okay, so you have, for achieving this, so you create a swap space. okay, IO separate swap space is there, so whichever programs you are using it, all that you put it in swap space, so that your input and output will be faster than the normal IO subsystem. okay, so keep a larger space for swap, okay, larger chunks. okay, so for this less management needed. okay, and then copy the entire process image to swap space. okay, so this will give an advantage. okay, so now demand page is from program binary on disk. okay, so that means, so don't take a page which has not been again converted to a object file. so once it is compiled, so get that from program binary. okay, so which is very helpful for you. okay, so this way you can implement the performance. okay, so then mobile system, so it doesn't typically don't support swapping. Instead it uses demand page from file system. so we are not going deep detail into this. so this points what we can use for optimizing the demand paging. okay, so then copy on write. okay, so copy on write. okay, so this allows both parent and child process. so this is one of a feature of the operating system. okay, now whenever we have a parallel process like our parent and child process executing, okay, so some of our code or pages are there which is normally shared between the parent and child process. okay, now if either process modifies a shared page, okay, then what happens? Now one is modifying, another needs no without modified page for its execution. so in that case, so suppose you think that child process has modified a page. okay, now parent needs a page which is not modified, but child needs a page which it wants to modify. in that case, now that particular page which is going to be modified no more will be shared. okay, so you need to have an extra copy of that. okay, so that is what we are calling it as a cow. so copy on write. okay, so which is you are creating another page, okay, on the write operation being done. okay, whenever the modification is done to a particular page, so only then you create a copy of that. okay, so that is called as a copy on write. okay, now when you have to create a copy on write another page of a modified page, okay, then where do you create for that? okay, for the faster access and all, you separate a separate pool of your free frames available, that is zero fill on demand pages. Zero fill on demand pages means that, okay, here you reserve the free frames. That free frames, okay, so will be erased off first. That means zero fill means it will be, see, normally any image in the memory will be zeros and ones. okay, any information will be a patterns, a unique patterns of zeros and ones. okay, so that means we are ensuring that, okay, the page whatever we are having already, if any modification was done, some page, the page is belonging to some other process, okay, that has already been some actions have already been taken. now everything you are terming it to be zero. That means the page is a clean page, it is erased page. okay, now the zeroed out page means it will help in many other advantage of memory leakages and all. so it is a erased page means that we are to ensure that we have ensured, the operating system has ensured that, okay, that page is not belonging to anyone, it is only belonging to the free frame of list. okay, so we are keeping a, so this will have an advantage that always the fast demand paging is done. okay, so this is how, okay, so this is copy on write what we are going to achieve. okay, so here you can see example. okay, so initially, so before process 1 modifies page C, okay, you have process 1 is there, process 2 is there, you have physical memory, page A, page B and page C. These three pages are shared between the process 1 and process 2. okay. Now when the process 1 is modified page C. Okay, now page C is modified, so this original page is to be still needed by process 2, that needs that copy, and this one wants to modify, and that copy is to be accessed by this. Okay, so now you have created another page, copy on write. Okay, you have copied this page on performing the write operation by this process, and this access will be given only to this particular process. Okay, so this access was given in the free frame, so this is created or copied onto a free frame of a 0 filled out pages. Okay, so now this is having a separate copy. This page when it is modified, this page when it is modified by process 1, so this is no more can be shared between process 1 and process 2, so we have created a copy on write. Okay. Now what happens if there is no free frame? Okay, so what actions the operating system has to do it? Okay, so there is no free frames which are used by the process. Okay, so it is in the demand from the kernel. The kernel is demanding for a free frame. Okay, it is a demand for having the I buffers, etc. Okay, so now when there is no free frame, what to do? Okay, how to allocate the frames for each process. Okay, so whether to give a extra page for that, or whether to over allocate, or whether to allocate less number of pages. So what is the criteria to allocate a pages and all that? So all these things we can utilize, okay, in the allocation algorithm. So we also have a page replacement algorithm, so which will decide which page to terminate. Okay, which algorithm you are going to use. Okay, so which pages have to be selected as a victim page, when you have to swap out, which place you have to replace out. Okay, so and how do you check the performance? Okay, so by putting the evaluating all the algorithms with a particular memory string. So for this, what we will do? Okay, so we use a page replacement this thing. So page replacement prevent, okay, over allocation of memory by modifying page fault service routine to include the page replacement. So that means over allocation you can prevent. Okay, suppose a process requires 4 frames. Okay, 4 pages. So 4 pages are fit into 4 frames. Okay, now if it requires 4, if you are giving 5, or if you are giving 6, that is called as a over allocation. Okay, so process is requiring, okay, particular process, you have a particular process P1 which requires, okay, 4 frames at a particular instant for execution. If you are allocating 6 to that, it is called as a over allocation. Okay, so now here when you over allocate it, okay, so it is consuming more memory. Okay, so for that you prevent over allocating. In case after 4 it requires some more, okay, then what you can do is, so get another new process, new page, by replacing some page. Okay, so that you can do it. So and then you use modified bit to reduce the overhead of page transfer. Okay, so that means, so if the bit was modified, okay, so you think that I am having like this. Okay, so now, so we are having a page. Okay, so we may be having page 4 pages of one process in the memory. Okay, so you are having page 0, page 1, okay, 2 and 3. Okay, so now after this is a page belonging to the process P1. Okay, now we are not over allocating at a time. The particular process is needing 4 pages, we have allocated 4 pages. Okay, so after that there may be some instruction which is referring to a page which is not belonging, which is right now not there. See, P1 is having, it may be having 10 pages. Okay, so P1 is having 10 pages in its virtual address space. Okay, but only 4 we are accommodating that. Okay, in the physical memory, so this is using 4. Okay, after some time it is accessing some more instruction, that page is not there. Okay, then you have to get that page into physical memory, and you have to replace a particular page, okay, somewhere which is not being used for a long duration of time. Okay, now what we have to do, whenever we have to replace, the replace means what, instead of page 0 you get new page. Okay, suppose you require some page 4 is required, so you think that this page was not being used for a long duration of time. Okay, now you are getting page 4 in this location. So replace means what, you move this page 0 on the hard disk, and then page 4 is brought. One is swapped out and another is swapping. Okay, so swapping out and swapping in is taking more time. Okay, so how can you reduce this? Okay, so you can do one thing. Okay, so you know that already all these copies of pages are there in the hard disk. Okay, now if this page was modified, only then, okay, this copy in the physical memory is different than the copy page 0 in the hard disk. Okay, so what we can do, if it is modified, only then you swap out this, okay, and swap in the page 4. If it was not modified, okay, this can be overwritten in this location, so that one swap out time you are going to reduce. Okay, so your memory IO is getting reduced. So this is done by making use of your modify or dirty bit. So page will be swapped out, this page 0 will be swapped out, swapped in. Okay, only page 0 if it was modified, otherwise only you swap in page 4. Okay, because this is read only page, it was not modified, so you can just overwrite this. Okay, so page replacement completes the separation between logical memory and physical memory. Okay, so where you have large virtual memory, okay, which is being fit into your small physical memory. Okay, now why do you need a page replacement? Okay, so here you have user 1, so you have page 0, page 1, page 2 and page 3. Okay, so here page 0 is stored at frame number 3. Okay, you can see frame number 3, you have H here. Okay, again you have page 1, so frame number 4. Okay, so where we are, this is a valid reference, so we have this instruction. So page 2, 0, 1, 2, so frame number 5, this is valid, so here we find J. Okay, now another page 3, it is invalid reference, this page is not there in memory, so this page is available on the backing store. Like that, we have another user, so page 0, so is found at frame number 6, so here you have A. So page 1, this is invalid entry, so this is found in the hard disk. Okay, so page 2, so here you have showing frame 2, so here you have D. Okay, so page 3, okay, page 3, here it is showing 7th frame, here you have E. Okay, so now this is how you are going to have the references, okay, shown in the physical memory. Okay, so now what is that basics, okay, page replacement algorithm, so that will be seeing in the our next video.